I'm Andreas Zeller. I'm the author of the Debugging book, and I'm here to present you a new chapter. The chapter we're going to look into this week is called Mining Function Specifications. And before you ask, what does this mean, mining function specifications, I will illustrate this right away with an example. Let me share my screen here and let's see whether things work. So which screen are we sharing today? Desktop 1, desktop 2, desktop 3. And miracle. Here we go. You should now be able to see a nice screen with the Jupyter Lab and stating mining function specifications. Konstantin, can you confirm?
Yes, all right.
Wonderful. Konstantin has a really bad internet connection, so I can always assume that if it works for him, it's also going to work for everybody else, which may be a gross overgeneralization, but I digress. Let's go right into our chapter right now. Topic today is mining function specification. And you wonder, why would I mine a function specification if normally the normal way of things would be I first specify what a function should do and then I implement it. Well, folks, sad reality is, in all generality, function specifications hardly ever exist. Most functions are written by programmers who don't take the time to actually document things, who don't take their time to actually document any assumption they have about their functions, who don't care to document any constraint on the inputs or the outputs of the function, no formal preconditions, no formal postconditions, no nothing, just plain code. This is the sad reality. And this is actually why techniques such as introducing assertions to a piece of code can be so super effective, because in most cases they are not even there. Now, the problem is that actually writing these specifications can be a bit of a pain. And a typical example for this is Python. Python is a language in which typing exists, but typing is being done dynamically, which means that types are checked only at runtime. If types don't work at runtime, then you're going to get a runtime error, but there is no static checking of types as you might know it from the compilation stages of a C program, a Java program, or an ML or Haskell program. So all languages with strong static typing, nothing of that kind in Python, which makes writing Python programs a breeze because you can just write things down without ever thinking about types, but which also makes it more and more difficult to maintain them after some time. I'm going to look into let's look into a very simple example here. We're having a function sum2, a plus b, there we go. And this returns the sum of a and b. But there is nothing that tells us which would actually be the arguments be of this function. So I can put into integers here and, oops, sorry. What have I done? Oh, sorry, it's called sum2, not sum, what am I saying? So here we go. Sum2 gives the sum of two integers, but I can also pass into floats. Well, converting integers into floats and possibly vice versa is a built-in feature of many languages, so nothing to worry about. But I can also come up and say, I want to build the sum of two strings in here, automated, and say Bob debugging, here we go. And then the whole thing nicely returns the sum of two strings. Actually, anything that is compatible here, anything which you can apply a plus operator on, will be valid. This of course is a recipe for, well, it's a recipe for lots of flexibility while writing things. But it's, on the other hand, it's also a recipe for trouble, because if you don't specify what the expected types of these functions are supposed to be, and if you don't check them at some point, then at any point, some other programmer using your code can start misusing your code, putting in other types, putting in whatever is compatible with the implementation. But then you want to change the implementation, and then all of a sudden, because programmers were programming against your implementation rather than some specification, all of your code suddenly breaks. So you cannot change your code anymore, which is bad, or every change breaks things. It would be much better if you would actually say, okay, I'm actually having a type declaration here, and I'm saying, well, A and B are supposed to be integers, and the whole thing actually returns an integer, such as this. And lo and behold, Python actually supports such annotations. It just doesn't check them at all. Well, or let's put it another way. It leaves it up to the programmer to actually check these. And there's packages in Python. There's the enforce package, which allows us to do this dynamically. And there is also the MyPy static checker, which takes the code of a Python program and does static checking on it, and actually then finds out that a call like this, which puts in strings, whereas actually here integers would be expected, then you're going to get an error both in the runtime checker as well as in the static checker. Now, a problem, however, is that Python programmers, and I'm no exception to that, actually don't like putting in types because, well, isn't it obvious what the types are anyway? I had a discussion with my PhD students some 2 years ago where I asked, should I put types into my Python code, yes or no? I'm sure you're all going to say yes, and then I'm going to put them in. And my PhD students unanimously said, no, don't put types. It's only going to be distracting, and it's going to be less readable. And I was very surprised at that, but that's how it is. And this is why the debugging book and also the earlier fuzzing book don't have any type annotations. Okay, I'd be happy to hear your comments about that, since it's not always, since you are the ones who have to understand all this code. Would it be better if you actually had type annotations? The world is open. Okay, but fortunately for us, there is a way to actually get those type annotations back, and not only get those type annotations back, but actually also get pre and post conditions for existing code right out of an existing execution. And let me just show you how this works first, or how this is being used first. And then we go into details on how this actually works in the background. So the idea is as follows. We're having a nice little package, which is called dynamic invariants. And this dynamic invariants provides us a class which is called a type annotator. Type annotator, okay, here we go. From dynamic invariants import type. When is it underlined? Oh, this is underlined because I haven't used it yet. Okay, and now I can say with type annotator, you'll see we're always using the same idioms here. It's always some type thing, or some with thing. And I'm using this as annotator. Here we go. And now the way I'm using this type annotator is I'm using this with actual calls, such as this one, for instance, 1 + 2. So, and what this type annotator provides is it provides a representation of the program that is compatible with all the executions we have seen so far. And the way this works is as follows. I can do this right away in here. We can do print, and then I use the annotator dot-typed functions. Here we go. And this automatically prints out a version of the functions that we have observed, and now with type annotations. So all I have to do at this point is I can go and replace my original definition with what I see here. For instance, I could go and copy paste this thingy here and put it in here, and now I have a typed version of sum2. So if you have trouble finding that Python code is not typed enough, there's ways to do that. So how does this typed annotator actually do this? Well, it's very simple. We have seen in this course how to actually track individual function calls and how to track individual arguments to these calls. And what the type annotator does is something very simple. It simply records for every function call that it sees, it simply records the types of every single argument there is. So in this case, we are invoking sum2 with 1 and 2. Both are integers, and therefore it learns that a must be an integer and b must be an integer too. What happens if I invoke this with two real numbers? So let's make a new annotator, and now we're invoking this with real numbers. Well, you won't believe it, and then it tells us that a and b are of type float. And if it turns out that we put in two strings here, for instance, 1 and 2, something like that, then it's going to luckily show that a and b are both strings and that the return value, which it actually also tracks, has a type of string. Now we can have some fun. We can also go and invoke this multiple times. Say, what happens if I invoke it first with, I haven't tried that before. So what happens if I invoke it first with integers and then with a double number? Then it's going to tell us, oh, apparently you can invoke sum2 with any type, and there's a special any type which matches anything, and the return value too is actually anything. So how does this work? And this is something you can look up in the book chapter. It actually works by tracking all these calls and by tracking all the types of all arguments. And interestingly enough, should you have a large body of code that is written in Python without any type checking, you can actually use this type annotator and run your existing code on it. And then it will provide you with actually type annotations for every single function and every single argument. Not so sure whether it also works for keyword arguments. That's something to discover. But it certainly should be able to provide you with all you need for positional arguments. So that's a simple thing already, and this gives us the key idea of this chapter, namely looking at actual executions, and from what happens in these actual executions, abstract into a generalization which actually holds for all current runs and possibly also for all future runs. So type annotator is something convenient, which is definitely for an untyped language like Python. But we can also get a bit further, a bit deeper into the possibilities here. And the second thing we're looking into today is another class which is called Invariant Annotator. Then you wonder, what on earth is an invariant annotator? An invariant annotator, ladies and gentlemen, provides us with not only with types, but actually with a number of properties that hold for all runs observed. And I'm going to illustrate that on with a number of calls on sum2. So let's make that 0 and, oh, well, not 0, there we go. And what does the invariant annotator give us? The invariant annotator doesn't provide us a method type functions, but instead it gives us a method functions with invariants. Oops, invariants. There we go. Let's see. And these invariants actually provide you with information on properties of the individual values. And I'm just slightly confused because this should give you a bit more than that. 1 second. Why is that the case? No, sorry. What's happening? There's something wrong in here. I don't know exactly what's wrong. That's what happens. That's 4 minus 5. So let's just take these two. I'm missing out one in here, so I'm confused. Okay. What this provides you is properties over the individual variables that hold for all runs observed. Here, we do have a precondition, and this precondition, we see that a is always greater or equal to 0, and this actually holds for all the runs we have observed. So in the first call, A is greater or equal than 0, and then the second call, A is also greater than 0. And we also have the same property for B. B here is also always greater than 0, so that's fine. And we also have a postcondition that holds. And this postcondition is actually a function over the return value and A and B, so it's the return value as well as the two input variables. And our postcondition here is that the return value is greater or equal to 0. So now now I'm actually seeing a bug in here, and I'm confused because we should also see another postcondition, namely that the sum of A and B actually is equal to the return value, and I'm just wondering why this doesn't come out here. But let's take a look into how this is actually achieved. So the way this invariant annotator works is that it actually, so we can look right into the actual implementation here. And the idea here is that you do have a set of properties. So let me just search for these. If this thing ever becomes reactive again, wonderful. Properties, isn't that set properties? One second, I'll be with you in no time. Yeah, that's all fine. We have our properties somewhere down there, that's fine. Okay. 1 second, my computer is almost breaking down. So we go for uppercase here, such that we actually find things. Oops. Yeah. Things don't exactly work as expected here. Here we go. This is what we're having. Okay, and these properties which we see here are all placeholders that get instantiated with individual variables, and then they are being checked on whether they hold. So in our example, we have seen here A is greater or equal than 0, and B is greater or equal than 0. This is an instantiation of this invariant pattern. X is greater or equal to 0, except that X, the big X here, is being replaced by the variable in question. And what this invariant annotator does is it takes these patterns and checks which of these patterns actually apply to all runs of our function that we have observed. So in our case, X is less than 0. Does that hold for A or B as seen here? No, so it's dropped. Does X less or equal than 0 apply for any of the variables we see in here? Well, less or equal than 0 is true for this run, but it's not true for this other run. So this is dropped just as well. And we do have quite a number of these properties. So we do have X is less than 0, X is greater than 0. We have X is equal to Y, X is greater than Y, and so on. We also have we also do have types in here. So X is an instance of the Boolean type, X is an instance of the integer type, and likewise. And we also do have invariant properties such as relations between multiple variables. And also, well, this is a typical Python fashion, a greater or less relationships between 3 variables. And we also have Boolean, such as X or not X, which, by the way, also translate into a list being empty or a value being non-zero as it is in Python. And we also do have X is equal to the length of Y, or X is equal to the sum of Y. So if there are properties like these over collections or strings, these also will eventually show up. So, and actually, since all of these normally would all be checked and instantiated, and I had tried this out yesterday, I'm just confused why we do not see these in here. So let me just do a little check here. Otherwise, we'll go into a bit of debugging, which is a bit boring. Dynamic invariants dot invariant. Upsala. Invariant. What is it? Invariant properties. Yes, of course. So let's see whether everything is in here as expected. Dynamic invariants. Properties. Okay, good. Import. Dynamic invariants. Here we go. And this is very interesting. Okay. Oh, this is super cool. I just found a big bug in my own implementation. This is really cool because when we're importing these invariant properties, for some weird reason, these later things here do not get added to that. Now that's really interesting. So let me just see whether I can rephrase this. Invariant, if I rephrase this to a properties plus. Okay, so that doesn't matter. We can just restart things here. Okay. And let's see, I have a suspicion on what might be wrong in here. So let's see. Yes. Oh man, this is a stupid bug. Really. See. If you just write plus equals. So let me explain things here. So we're having a special importer here, which allows notebooks to import each other. But when we import things, we're having a special pattern such that we don't just rerun the entire notebook while importing it, which normally would be the case. That's not what we want. But instead, we're only importing cells that follow a particular pattern, and the cell pattern that we are looking at is either it is a definition of a function, or it is a definition of a class, or it is a global variable. And a global variable must follow the pattern, a name in uppercase letters followed by an equal sign. And plus equal is not it. And this is why the very example which I've just shown you wonderfully works when we are within this notebook, but not when we are importing things. So good I found that, because otherwise you would have wondered, oh man, why can Professor Zeller do all these magical things in his notebook, and why can I not import all these things into my notebook? Yeah, what a pity. Okay, good. Let me just fix these things, and then we can actually look at the full set of notebooks. Here we go. 1 and 2 and 3. Okay, that was a quick fix. Oh, forget about override. So we override things wonderfully. We have things fixed. We restart things. See, this is live debugging, ladies and gentlemen. We are fixing things as we're fixing things right in the notebook while we're talking. And now we finally have all the properties that we're checking, and you see the whole list. And now that is when you actually see the full set of invariants. And okay, good. And that's actually, and now you see that there's quite a number of invariants that all hold for the runs that we've seen. So we see, for instance, always A is less or equal than B. And we also see that always A is greater or equal than 0. And interestingly enough, we also find that there's a postcondition. The return value is always A plus B, which actually is precisely the return value we want to see. And what we also have is we also have type checks in here. A is an instance of an integer, and B also is an instance of an integer. Okay, so The trouble with dynamic invariants is that we are limited to the incompleteness of dynamic analysis. That is, we can only look at what we have. And therefore, we do have quite a number of false over approximations in here because, well, the fact that A is less or equal than B need not be the case actually for some two. There's no need to do. It just so happens that we had that in our very set of runs. So of course, as soon as I add another call where this is no longer the case, then this precondition magically and immediately disappears. And what we also can do is we can also add in some negative values just for the fun of it. And then we also get more preconditions that disappear. And now, because all these greater or equal than 0 or whatever disappears, and now we actually do have a set of invariant candidates that actually make more sense. Because what we have now is the return value is A plus B, which is actually the post condition as it should be. We also do have that the return value and that A and that B are all instances of an integer, which is also how it should be. Well, it depends on how you want to define some too. But if it's only used with integers, then that's what you get. And we also have these A is the return value minus B, which of course is implied by the other post conditions as we have them over here. Now, if we go and invoke this also with, floating point numbers, just for the fun of it, then we will find that how the set of post conditions further is reduced. And now they have the one interesting post condition, namely that the return value is equal to A plus B. Downside of the whole thing, you won't believe it, but this actually also holds for strings. So if I put in A plus B, then, oh, sorry, not A plus B, what am I saying? A and B, here we go. Then you will find that this post condition return value is equal to A plus B still holds because this is a pre-post condition that also holds for strings. The post conditions with B plus A, however, does no longer hold because in strings, the plus operator is not commutative, and also the post conditions which we had previously with a minus, as we had them when we were only looking at numbers. Here we have them again. These also no longer are there because, well, minus does not apply to strings, at least not in Python. Okay, but that's something we'd like to avoid here. And of course, well, let's stick with integers such that the invariant annotator also gives us pre and post conditions for inputs. And again, the way this works is by taking these patterns, and you can actually add more to these as you like, is to take these patterns and instantiating them every time with every call and every combination of variables, and retaining those instantiations of these patterns that hold for all runs observed. And this can then give you nice candidates for pre and post conditions, assuming, of course, that you do have sufficiently many tests. Now, how is this being used? In particular for debugging, but also for testing? Well, there's multiple uses of specifications. The first thing, and that's rather obvious, is you can throw this right away in an assertion checker of your choice, convert these preconditions and post conditions into checks. Actually, this is actually already being done here. These post conditions and preconditions are actually implemented. This is actually code, yes. These are actually implemented as function transformers, which add a check at the beginning and at the end of the function, checking whether they are satisfied. I think I can take this entire blob of code here and execute it. So if I do this, can I do this? Oh no, I don't have precondition and post condition. So what I need to do is I need to import these first. So let me just see whether this works. So from precondition and post condition. And here we go. And now if I execute this, Now, something magical will have happened. These precondition annotations here will have automatically modified the definition of sum2 such that there would be automatic checks being applied whether all of these preconditions and postconditions actually hold. And if I now invoke sum2 with well, things that do not match these learned preconditions and learned postconditions, then I'm going to get an assertion error. The precondition is violated because A is not an instance of the integer class, the integer type. Likewise, if I modify sum2 to do something different, say no longer adding things, but actually multiplying things, now I put in here, well, one and one would be one and one actually works because if I now invoke 1 and 1, and then it will automatically determine, well, this is a blob of things. It will automatically tell you, I just violated the previously learned post condition, namely that the return value should be A plus B. And ladies and gentlemen, 1 times 1 is, as we all know, is 1 and certainly not 2. So let's fix things back here. So convenient, automatically gives you assertions, and these assertions can then catch errors. This can be helpful. I mean, this can be helpful, especially when you're having a change to your code. So you're taking the old version of your code, you're putting in these additional assertions, and then you take the new version of your code, the one that fails, let these assertions run, and you will immediately find out where things are different and violate what we have seen before. The second big usage of such learned, pre, and post conditions, and actually also type annotations as we have seen them before, is for formal verification. For formal verification, you need to know what individual types are, that's obvious, but you also need to know what a precondition is in order to formally verify that a post condition holds. So again, pre and post conditions are super important for that. And these also serve as documentation, by the way, for your program, because, well, it also in addition to types, they tell you what is expected from your function. So that's also very useful. And finally, and you will see examples to that in the chapter, you can also use them to find out which under which conditions something specific happens. So you take only failing runs of your function, and then you find out what are the pre and post conditions that apply in these failing runs, and maybe why are these conditions different from what I have in passing runs. This can also be super interesting. So this builds a nice bridge between dynamic executions and static checking, or runtime or continuous runtime checking, or also static analysis of your program or symbolic verification. But let's not forget, there's also limits to the whole thing. And the obvious limit is that you do have a finite set of properties to check. So of course, these are important properties, knowing about the range of individual variables, knowing about plus, minus, basic arithmetic functions, basic relations. This is all neat, okay? But if you have a function that fails, if you have a function that fails on a full moon, for instance, okay? Well, the full moon, what is a full moon? You have a function that fails on Easter, and then you would actually need a formula in here that says, is Easter of X, or has some particular property of X, or anything related to date, time, whatsoever. All the specific domains in which your program might operate that go beyond these generic domains that we see in here, none of this would be covered. And indeed, you would have to go and extend your vocabulary of properties towards the specific domain in which your program is acting. And by the way, this is one of my all-time favorites. When I am saying that, oops, what happened to my A plus B here? when I am saying a program that only fails on a full moon. This, ladies and gentlemen, actually has happened. This actually, and it actually was different. This was a payroll, an employee payroll function that failed on all days except for Wednesdays. So when you ran it on a Wednesday, it worked, and if you ran it on any other day of the week, it would fail. Now, why would something fail only on a Wednesday? Well, it's very simple if you think about it. What happened was there was a string in the program which would actually take the number of days, okay? So that would be Friday or Sunday or Saturday, okay? So not too complex, right? So these are things which we would have. And now the interesting thing would be that Wednesday has a particular property, as you can easily see in here. It is actually the only day in the week that has 9 characters. And what happened was that the day of the week was stored in a field which only had 8 characters. So there would be an overflow from the field in which the week of day was stored, this 8-character field, into the next field. And this next field in memory of the program happened to be a Boolean value. And this Boolean value was normally actually also erroneously initialized to N for no. However, when on a Wednesday, this magical field would be overwritten and become a Y for yes. And only if this field was set to yes, which was another error. So this first error, this buffer overflow error would cancel out the other error, namely of this other Boolean flag here being erroneously set to N for no. And only then would the payroll actually be printed. So you can already see how the property of particular variables can affect the outcome of a program. And if you extend the set of, if you go and extend the set of properties towards something that says, let's say, length of X is greater than length of Y, here we go, or actually greater or equal, doesn't matter. As soon as you have such a pattern in your set of invariant properties, then this property may be instantiated as length of Wednesday is greater than the length of the day of week. Or actually, the way it would really look like is input day of week. So this is the string that would be input, and this is the string which would be used to store it. And this, ladies and gentlemen, is a property that would hold only on Wednesdays. And if you now mine those invariants for those runs that pass and those runs that fail, then you would find out that on runs that pass, then this property would hold, and on runs that fail, this other property would hold, giving you an important hint on why the program failed. Now, this is mining invariants, and this is actually just a short, well, a small fraction of what actual dynamic invariant miners can do. The mother of all dynamic invariant miners is the so-called DICON tool by Michael Ernst and colleagues, in particular, Bill Griswold, David Notkin, but the true genius came from Mike Ernst here in this case. And he was the first person ever to actually come up with such patterns and see whether they can be instantiated and see whether they hold. And his work on DICON has been shown to be highly influential in the field. Is one of the most frequently cited papers in debugging. It's one of the classics in the field. And with the implementation which we have here, this has far fewer features than Daikon. Daikon is far more sophisticated than that. But on the other hand, it allows you to experiment with this on your own. And this is precisely what I'd like you to, what I'd like to invite you to have a look at the implementation, have a look at possible usages, and try out how dynamic invariants can help you figuring out what a particular piece of code is doing and what the weaknesses are, but also what the strengths are. With that, I'm happy to have concluded today's lecture. Now with a real bug. Finally, I always have been waiting for this. I have had a real bug in a lecture, and I've been able to fix it right away. Oh, I'm a genius. I should become a professor of sorts. Oh no, that's probably not what I should do. Maybe I should work harder on creating code that actually works. Well, this will now be fixed, and from now on, you won't have any trouble with that. Okay. That's all for now. Thank you very much for your attention and have fun with invariants.